Good day, folks. I hope you watched my last video regarding chemical self-regenerating reactions and where this was taking me. I wanted to introduce the concept before I get right into this. So basically what I want to talk about next with this into consideration is the everlasting flame concept. And I know the scrutiny and all the screaming, I could hear it from here. It's all myth, it's all legend, it's all BS. Well, you know what, folks? They say that the ancients was doing it, thinking of that. It can't be that complicated, right? And of course, when I started thinking about the chemical reactions and started doing some research into it, believe it or not, folks, do not laugh, but in theory, there are multiple possibilities. And not just one path, but about three really promising paths, and I want to talk to you about this. So I'm going to share the idea with you, which could really be a game changer in certain conditions where you have to be off grid and everything. So first thing first here is I'm going to start with basically the introduction here. So this is basically the easiest method. I've figured out three potential methods. In theory, it all drives, folks, which is very interesting. So I'm going to start here. So we need our regenerating fuel, okay? So as I said, we want to take advantage of self-looping chemical reaction, but our version of asymmetrical regauging has to come from stuff that's already available that we don't have to pay for in the environment. So the chemical equivalent of that. So we want to generate and regenerate our fuel. So taking that into consideration, we want to take advantage of the moisture in the air. We also want to take advantage of the ambient gases such as oxygen, nitrogen, and etc. The reason is we want to trigger a slow oxidization effect. And of course, we have to keep a catalyst in mind because this will lower the activation energy, which is a benefit, and lower the temperature reactions required chemically to sustain our looping reactions. Now, of course, now going into two, we're looking for the reaction. So the actual reaction in theory, folks, that could work is the addition of calcium carbide, CaC2. So what you have here is CaC2 plus 2H2O, which is acetylene gas, essentially, more into that later, plus CaOH2, and that's calcium hydroxide, okay? Why, you may ask? Well, CaC2 will react to the ambient moisture. The byproduct you get from that is a very, very low acetylene gas, just enough for a flame. So C2H2, this gives us our slow flame conditions. Now, while the flame burns, we get CaOH2, which absorbs the CO2 from the air, and that'll convert it back to CaCO3, which is calcium carbonate, a form of it anyways. Now, because the flame is burning, thermally decomposes back to CaO and reacts within the carbon to form CaC2 again with the help of the flame heat. So that's one way of doing it. And essentially, you would need to provide naturally the ingredients for this, right? So essentially you need about 500 grams, let's say, of the calcium carbonate. This, in theory, could last many years, maybe at least 2, but you would intermittently need to reprovide some of the source, right? So it's not a 100% at this point, but it takes advantages of a form of partial looping to slow it real down, so your 500 grams will last a long time. So it's a step in the right direction. We have a concept now for a flame that will last a matter of months and years. Can we enhance that? Yes, we can. I will show you method number 2, folks, so stand by for that. Alright, folks, here's a second approach here for better reaction, but the downside is the process requires a little bit more of a controlled environment. But for conversation, I'd like to talk about it as well. So here's an example, this time using slow oxidization of metal fuels. So we're looking for specifically, not limited to, but but these types of reactive metals, in this case magnesium or zinc, okay? So essentially in the presence of water vapor and oxygen, the metal slowly oxidizes, and that gives you heat in an oxide layer. And this oxide could be reduced back to metal by secondary chemical processes like I was talking about earlier. So with the help of a reducing agent or heat from the flame, of course. So what that means is essentially, in a simplified form, a wick coated with magnesium powder can slowly oxidize when exposed to air moisture, creating a faint glow. The resulting magnesium oxide, MgO, can be reduced back to magnesium using carbon with high flame temperature. So a kind of self-looping mechanism, but again, taking part of its energy from the environment. Once the burn starts, you still got to light it up, but once it gets going, you get that self-looping reaction. So again, a better approach, but again requires more calibrated environment to make it work. But just for the sake of discussion, I wanted to talk about this because it offers a more efficient way of doing it. So now we're actually getting somewhere, but we still don't have our 100% self-looped system. I'm getting there. So let's get to the next example. So I figured out roughly 3 ways of doing this. So we're not limited to just. It seems like, I guess what I'm trying to say, folks, is the more you start thinking and experimenting with this, the more you can come up with practical real-world scenarios that could actually work. So next example. All right, keeping the best for last, the grand finale one. Here, the one that everyone is looking for here, which I was trying to build to it because I needed to explain the other interactions first. But the one that everyone is really looking for here is the thermochemical looping reaction. So example, iron-oxygen loop. So essentially what we're getting at here is a wick coated with iron nanoparticles that alternate between iron and iron oxide, so Fe2O3. So essentially it's really neat because as you get into this, you kind of see like the similarities where in the electrical system we depend on nonlinear systems and breaking the symmetry and that kind of thing. You start realizing that it's the same systems in their own domains, but different applications kind of like here, we're doing the nanoparticles that alternate between iron and iron oxide. It's a form of breaking the symmetry. But what I'm getting at, the chemical equivalence, which gives us the same end result. So there's a universal aspect is what I'm getting at about all of this. So once you understand what you're looking for with the electrical systems and you start messing around with the chemicals or the mechanicals, it's essentially the same concepts for triggering mechanisms and regauging and whatever. You're just playing with the compatible energies within that domain instead, in whatever form they happen to be in. So moving on here, what you get is when exposed to air, the iron oxidizes very slowly, giving you the slow heat and the reaction. So you got to start with lighting the wick, obviously. The resulting iron oxide can be reduced back to iron by a reducing agent. I talked actually about that with some of my previous power cells, the silicone metasilicate, not silicone, sodium metasilicate cells, I'm sorry, and how to make a redox reaction. But there's several chemical ways. So I give a quick example here, hydrogen or carbon monoxide. So essentially, all of this gets generated in a mix and we integrated from ambient sources and or carbon dioxide. It depends. There's many ways to build this stuff, you see. So I'm giving you the pure theory, and I'm sure those who have more of the engineering, mechanical, hands-on can figure out, already interesting candlelight configurations, right? So what I'm getting at is, even the people who are into building candles should really be interested in this, because I understand in theory, right? Even the fewer ones, the first examples I gave you, even if you make, a half attempt at that and it works even 25% because it's not efficient, you didn't do it exactly right, but you still get all that, for manufacturing purposes, wouldn't it be nice to have a candle that lasts 6 months instead of 2 weeks, So for the regular candle people even, the more simple, they're not necessarily the thermochemical looping, but the simpler ones that offer more long-lasting mechanisms could be something worth exploring. Not my domain, but just putting it out there, right? So with that said, the reaction, obviously, in the thermochemical looping reaction, it could actually be indefinite as long as the loop can sustain from the ambient inputs like the CO2, the oxygen, and all that. As long as those elements are there, once you light it up, it could keep going. So very, very interesting. But some key points here, if you are going to try and attempt to build something like this, we must use a catalyst. There's a lot of ways. There's platinum, there's palladium, there's rhodium. So you would incorporate that into the wick to lower the idea here is to actually lower the activation energy all of this takes through the use of a clever catalyst. So summarizing it, we want controlled moisture tank or intake. We want a catalytic wick, as we described here. And it's basically thermal recycling is a big part of this. And of course, the environmental placement for best ambient interaction means a lot. So depending on what chemicals you're going to use and whatnot. And this stuff here, Bedini was a lot into this stuff. And depending how you want to look at it, maybe on the light side, even a light form of transmutations, you see, we're getting... But in our sense, Bedini used electrical triggers and heat and everything to get transmutation. But I guess it depends which way you look at it. Chemically speaking, it's quite a natural thing to be able to use external reactions to come up with a new element, right? So in a way, nothing new here, but it all depends on which way you want to look at it, right? Which side of the coin you're on, essentially. So with that said, folks, I want to move on to the next, because now, okay, we're able to get a flame, but people would like to be able to do something with that flame. So I'm going to show you optionally, how one could generate a little bit of electricity with this concept. Again, what everybody wants, right? So I thought about that too, so I'm going to present that next for you folks, so just stand by. All right, folks, so now we've built our candles, so what could we do with this apart from getting heat and long-lasting flame? Well, some people want to collect and try and do heat energy, so they have thermoelectric generator modules, TEGs they're called in short. So essentially the hot side gets exposed to heat and the cold side, usually a cold heat sink. So typically these TEG units generate around 5 volts to 200 MA. It varies a little bit from part number, model, and size, whatnot. So the general idea here is your special candle, your flame, and around here a sort of casing with a metal heating element that heats from the flame. The hot side of the tag comes directly on it, and then we have our heat sink, our cold heat sink on the other side, and this provides us roughly our 5 volts 100 MA. Now, of course, this may take about half an hour to heat up, so once it gets going, then you get your nominal voltage. So it's not an instantaneous effect, but it builds up once you get the heat. So optionally, there's better ways to design this. I do a kind of mask, maybe with something inside like an oil or something that won't bubble and burn with the heat, that can retain the heat, and we can just a more efficient way to keep the heat and perhaps sneak a few of these tag modules on there. So essentially what I'm getting at, it would take anywhere from 6 to 10 of these modules to generate anywhere from 5 to 10 watts with our everlasting flame concept. Now you're all saying, great, let's do it. A few issues, folks. For an individual to get all the chemicals and everything ready for this and to do trial and error and to experiment, you may be looking at 2,000 or more for someone like me to just start experimenting with this. And that's not counting the all of the chemicals and the components that I need to buy. So because I'm just an individual, like most of us are, we don't have access to wholesale pricing, nor do we have the factory environment. So what would happen is it would cost me, like for example, the other one that used 500 grams of a component here. It would What would happen is this is I'm not trying to give you all bad news, but it would cost about $240 for me right now today. That's assuming I had the setup to build this candle. So what I'm getting at is, let's say, as long lasting as it is, let's say 3 years, okay? At this amount, if you were to do the math of how this could give energy, I'd actually be about $100 in the red of how much money I had to put in here versus if I'd pay the mains for it. You see what I mean? But the upside is it's off grid. It could work anywhere. I don't have to depend on it, right? However, if I'm a factory, I have a setup and I've got access to wholesale, I did some calculations. All of a sudden, the price drops to $6 to produce one of these setups. That's with the tag and everything built into it, ready to go. So now, if I am a factory and I'm making these kinds of generators, and let's say it's only costing me $6 to build, let's say, a 10-watt system, and let's say I sell that for $100 retail, okay? Well, somebody who's going to spend $100 on this, it's not so bad because within maybe 3 months, it has paid for itself of what they would have to pay in electricity, yet it still keeps going. So what I'm getting at is after 3 months, let's say you get 4 or 5 years out of it, at 6 months, it already paid for itself, assuming we can put this in a retail environment. But perhaps this is why nobody's experimenting with this in an individual basis, because apart from needing the setup of thousands of dollars to build this stuff and the wick and the cutting and the machining and all that, you need to get all the chemicals. And if you don't have wholesale pricing, this is going to be a very expensive project. But I just wanted to put it out there, folks, for the information. The theory is there. One could really do this if they want to. And that brings you to what I've been talking about. Maybe you don't need 6 to 10 of these. Maybe one version, maybe 5 volts, 100 mA. If you're using it as a trigger, some of the current and RF mixing applications, and this could be your power source, and you're going to use the environment to top it off, you might not need all this extra. This might be the perfect trigger for you if you don't have hydro, if you don't have wind, if you don't have solar, if you're literally in a cave or something. This might work for you. So again, depending on the application, and there's definitely something there, and I just wanted to put it out there for you folks, and I hope the information does you well. And with that said, folks, until next time, and thank you very much. So, folks, I hope that was interesting for you all. And I wasn't going to mention this last part, but as I was editing the video, I realized that I apparently let it slip without warning at the first introduction video. Literally at the end when I say, okay, that could be your fuel source. Well, that's the key point. If you read between the lines, I gave you the candle example, but one could really go big with all of this, with these specific reactions and others as well. And what you can get is basically a home or factory style home garage, whatever, a factory of a fuel source that is basically very inexpensive, that would use mostly environmental triggers to produce that fuel. So basically a major shakeup of society, and maybe some dangerous thing to get into. So maybe it wasn't the smartest thing to mention it, but again, that's why I didn't want to say it initially, and I wasn't, but since I let it slip, I figured, well, I may as well say it now because someone's going to ask, what did you mean fuel source? So essentially what I'm getting at is, instead of actually, building the candle and everything, you do the same concept, but like in a home garage lab kind of setting, in a big hall, essentially controlled environment, where you would set up your reactions, but in much bigger form. But what that's going to do is you got to remember your reactions are going to trigger much more CO2 output. So you got to think, the same way we're already thinking. So how could I take advantage of all these natural systems? Well, you're going to maybe, let's say, find special plants that have an abnormal property of converting the CO2 to oxygen very efficiently. So you'd set up your hall with all of those plants in there where they're interacting with your massive chemical plant interactions, eating up the CO2 and giving you oxygen back in return. And as you see, the oxygen is something it needs too. So you're giving it naturally the oxygen back so it can sustain that loop reaction. You end up getting your byproduct, which is a fuel source when you're done and over with. But the plants have an actual lively application into it. And essentially, if you go further than your nose with it, you can find, plants that have advanced features in its sap, for instance. You could use the sap properties for the catalytic effects that you're needing. So essentially, you come up with a brew of that sap, and from what I can see of all the reactions that are happening here would probably be some form of a carbon byproduct that you would end up at the end mixing together, and that would probably smell something like charcoal. And you can just add some water in there, and as you can see from the reactions, that would complete the reaction and you would get your compatible fuel source. So just food for thought. This really reveals a lot once you start interacting with these specific chemical reactions. And again, thank you all for watching, and I hope this sheds light.